Hi, I'm John Norman. Today, we will be talking about two separate and distinct topics: fires in buildings under construction, renovation, and demolition, as well as fire-related emergencies, such as oil burner emergencies and gas leaks. Buildings under construction, renovation, or demolition present unique challenges to firefighters. Fires in these type of buildings can result in substantial loss and account for a large percentage of firefighter casualties. That shouldn't surprise us, because during any of these three phases, conditions are ripe for fast-spreading fire. Large quantities of combustibles are often left exposed. These include piles of lumber, cardboard boxes, sawdust, wood scraps, and other refuse, as well as exposed floor, wall, and roof joists. Flammable materials are often present, like adhesives, sealants, and finishes, as well as fuel for temporary heating. There are also plenty of sources of ignition available at construction sites, like welding or cutting tools, portable heating units, and temporary wiring. When one of these sources of ignition reaches a supply of fuel, rapid fire spread is likely, due to the unlimited air supply inherent in open, windowless buildings. In addition, many of these buildings lack fire protection components that would be required in an occupied building. Sprinklers, standpipes, and fire doors may not be functioning or even present. Fortunately, major fires in buildings under construction aren't a common occurrence. Most sources of ignition are usually removed at the end of the day, when the construction crew leaves the site. In addition, power to the area is often cut at the end of the workday and not turned back on until the construction crews return. It is also common practice to post a fire watch in the vicinity of any hazardous operations, like torch cutting. This person should remain in the area looking for signs of hidden fire for at least 30 minutes after the hazardous operations have concluded. There are plenty of reasons that buildings under construction present challenges that firefighters don't see in regular bread-and-butter type fires, or even during a normal high-rise operation. First of all, many buildings under construction will lack any firewalls until the later stages, meaning that the entire volume of the structure is exposed to any fire that begins. The floors often have large penetrations that permit worker access and passage of construction materials. Due to these holes, extremely rapid vertical fire spread is not just possible, but likely. Firefighters need to be especially careful around these holes, as they're often not visible under fire conditions, and any type of guard around them could have been destroyed by the fire. Often these holes will be vertically aligned, allowing burning debris from the fire floor to rain down on any firefighters climbing up through them to reach the upper floors. Even though these openings permit rapid fire spread, they can also aid firefighter operations. The holes in the floor will allow for effortless ventilation, and the lack of partitions allows a hose stream to sweep an entire area for its full range. If you are faced with a fire in a structure of this type, the stream of choice is an elevating platform stream. You can avoid sending firefighters into a potentially dangerous minefield and still deliver a high-volume, long-reach stream that can knock down an entire floor of fire. Although it is an excellent stream for serious fire conditions, you need to take some precautions before deploying it. Your first concern should be clearing all personnel from the streets below and on the opposite side of operations. A large hose stream can send tons of debris showering down on surrounding areas. Items weighing more than 100 pounds can be propelled by a 2-inch solid-tip elevating platform stream. You may also have to vary the usual sequence of stream operations in order to cut off fire extension. Normally, when fire is present on multiple floors and an elevating platform is to be used, it would start on the lower floors and progress upward. Steam produced on the lower floor will rise and aid extinguishment on the upper floors. Finished buildings also have a much slower rate of vertical extension due to fire stopping or vertical openings. In buildings under construction, however, none of these conditions exist, so start stream application at the highest involved floor and work down in these open buildings. First off, steam won't accumulate in a wide open building, so its extinguishment effects are non-existent. Second, vertical fire spread may be so rapid that it could progress upward beyond the reach of the stream while you're still fighting fire on the lowest floor. Finally, if you attack the upper floor fire first, some water runoff will pour down the myriad vertical openings and aid in checking extension on lower floors. Another consideration you must evaluate when approaching a building under construction is access. Whereas a completed, occupied building may have 3 or more staircases for access to upper floors, a building under construction may only use a single set of construction ladders made of 2x4s. It is common practice to remove the lower ladder at night to prevent entry to upper floors by vandals and children playing in the area. Usually, if a fire department ladder is put up to the second floor, the remaining floors will be accessible using the remaining construction ladders. Still, it may be treacherous to ascend to upper floors using one of these ladders, especially while carrying tools or a hose line. Some of these ladders may project through the future elevator shaft, meaning they can run from the basement to the roof. A fall off a ladder into these shafts could result in severe injury or death. Because of these dangers, it is usually quicker and safer to access the fire floor using the department's ladders, either aerial or portable. Most buildings that are higher than the reach of an aerial ladder are usually provided with hoists, similar to an elevator. Unfortunately, hoists are often also shut down at nights and on weekends when the construction crew isn't on site. In addition, there are usually 2 different types of hoists, one for people and the other for materials or equipment. The equipment hoist won't have any of the controls in the car. It is controlled by an operator from the ground, and it lacks many of the safety features found in passenger elevators. It should be avoided at all costs, so make sure you're using the proper hoist. You should also be on the lookout for large quantities of flammable liquids or gases. Liquefied petroleum gas is used to fuel salamanders, tar kettles, torches, and other devices found at construction sites. Dozens of LP gas containers may be present at larger jobs. When pouring concrete in cold weather, buildings are often wrapped in plastic sheeting or tarps to keep heat in and the elements out, thereby speeding the curing process of the concrete. Another issue you may have to face is that the fire protection systems don't always keep up with construction. Sprinkler systems are often some of the last items completed, since the heads can't be installed in hung ceilings until after the ceiling itself has been installed. The same may be true for fire doors and partitions in areas that aren't rented out yet. At a bare minimum, the standpipe riser and outlets should progress to within 2 floors of the highest level under construction. This is usually a required part of many construction codes, but it often gets overlooked. Even if the standpipe riser is progressing as planned, it may not be kept wet. If this is the case, you will likely only have a fire department connection, unlike any with which you are familiar. This FDC may be the only source for putting water into the system, so be sure it's clearly marked, unobstructed, and that all fire department personnel are familiar with its location. First arriving units at a fire in a building under construction should always test the first floor outlet for water before proceeding upward. Riser control valves can render the system inoperable on upper floors, so be sure to check for water flow as you go up. When you get to an outlet that has no water, go back. The shutoff valve will be somewhere between the last outlet that has water and the first one that doesn't. Buildings under construction or renovation are more prone to structural failure and collapse than those that have been completed and occupied. This is due to a number of factors, including the lack of a roof or floor. When fireproof coatings or membranes haven't been installed, steel members may be exposed to rapid rises in temperature, which could lead to their failure. Steel I-beams and columns will often receive a spray-on fibrous coating that is supposed to protect them from extreme heat. If this coating is missing, steel will fail at approximately 1,500 degrees. Many so-called non-combustible buildings also rely on a hung ceiling to provide a membrane-type fire resistance between the occupancy and these unprotected steel members. Since these tiles aren't usually installed until much of the construction has been completed, even this minimal fire resistance they provide won't be present in buildings under construction. Steel bracing cables are used during construction to provide temporary support until more permanent bracing or framing is in place. These cables will fail readily when exposed to fire and can lead to extensive collapse. Because of this, a heavy fire in an area where steel cables are used extensively demands either immediate cooling of the cables or prompt evacuation of the surrounding areas, including below. Probably the most serious collapse threat in buildings under construction comes from structures that, when finished, would provide the greatest resistance to collapse: poured in place, reinforced concrete structures. Concrete takes about 48 hours to dry and cure, during which time it has almost no strength and it is held in place by a wooden or fiberglass mold. The floor below the most recently poured concrete can be a veritable lumberyard of plywood and 4x4 posts. There is also usually a lot of scrap wood and sawdust lying around from the cutting and fitting of the framework. On top of all that, the ceiling is made of plywood that has often been treated with a combustible coating to keep it from sticking to the concrete. Because of all this, any fire originating in or extending into this area will spread very rapidly. A failure of the 4x4 support post would likely lead to a collapse of the entire mass of concrete they were supporting. If this collapse begins, you have to worry about the weight of that mass of concrete and the formwork crashing down onto the floor below and overloading it. If that floor in turn collapses into the next one, it could set off a chain reaction that goes all the way to the bottom level. A collapse of this kind took down all 27 floors of a building under construction in Bailey's Crossroads, Virginia. This collapse resulted in the death of 14 construction workers, but it could just as easily have been firefighters had a fire precipitated the collapse. It appears that a worker prematurely removed a critical shore. It takes concrete about 28 days to reach its greatest load carrying capacity. However, the plywood formwork is stripped off to be reused on higher floors after just about 48 hours. For the next 16 to 20 days, the floor still needs to be braced with 4x4 posts every 8 feet. The shoring should indicate to you that any fire on or above these braced floors could cause a collapse. Once the concrete is cured sufficiently to allow removal of all the 4x4 supports, the threat of collapse from fire exposure is greatly reduced, but not completely eliminated. No matter how old concrete is, it can still be subject to spalling when exposed to heavy fire. Spalling is the separation of concrete chunks with explosive force when water trapped inside the concrete expands and turns to steam. Substantial chunks, some weighing 100 pounds or more, can collapse as a result, but spalling usually only occurs under direct exposure to heavy flame. That means it's unlikely that a firefighter would be in the immediate vicinity with such a large quantity of open flame and no operating hose stream. There is a growing trend to allow part of a building to be occupied, while construction on the rest of the building continues. This practice poses a great challenge for firefighters. A building under construction doesn't generate positive cash flow until its units are rented, so there is great pressure to get tenants in and paying rent as soon as possible. Many times, the more desirable upper floors are rented first, leaving the lower floors unoccupied. These lower floors are then used as storage areas for construction materials, while the crews are finishing other areas of the building, creating a heavy fire load. That problem is compounded by the fact that most construction codes allow these areas to remain unsprinkled as long as they're not occupied. The feeling is that it would be unreasonable to ask the builder to have sprinklers in an area where no tenant is paying for them. I call that utter nonsense. If builders object to installing so-called temporary sprinkler systems, you should simply forbid the use of any floor above the level where all fire protection systems are not operational. This may seem harsh, but it is the only way to ensure the safety of the occupants above, as well as the firefighters that would have to attempt to rescue them. Remember that fire spread is especially rapid in buildings where work is in progress. The most dangerous building in the United States to fight a fire in is the vacant building. The firefighter death rate at vacant building fires is more than 5 times that in occupied residential structures. This is due to many factors, including old age, damage done by weather, vandals, previous fires, removal of structural supports during renovation or demolition, and the rapid fire spread created by the removal of doors and other fire barriers, such as ceilings. How do you stay safe at these structures? It takes a major attitude adjustment. Just because it looks like a building doesn't mean that it should be treated like a building. Particularly in the case of buildings undergoing demolition, these vacant buildings are nothing more than a pile of rubble that's going to be carted away in the next day or week. When we finally get into this building, it's a big 6-story H-style apartment house, vacant for years and years and years. Things are not going well. All of a sudden, just a blast of fire runs down this hallway, and now we're all scrambling. There's my company and an engine company and probably another couple of guys from a couple of ladder companies up there. And now we're all trying to retreat toward the front, and it gets bad suddenly. And I end up getting just kind of shoved backwards into the staircase going down, except there was no staircase. It was just a shell of a staircase. I just end up going straight back down into the staircase, and there's no stairs there. There's no treads. The steel risers that would normally support the tread are the only things left. All the marble treads are gone. And I end up hung up my leg. One riser is holding the front of my leg, and the other riser is behind the back of my one calf. And I end up just face up, but facing backwards downhill, laying down this staircase. And there's only about a handful of risers, and I actually have a picture of it, a handful of steel risers left. And I drop my hand light, and I see the light disappear down into this black hole underneath me, and I drop my hand tool, and I'm listening, and I'm hoping it makes a noise after just a second so it doesn't fall far, but it's falling and falling and falling, and I'm not hearing anything, and I just keep seeing the light disappear further and further down. And with that, 2 other guys, my driver and the officer of the engine company that was waiting for water, end up knocked into this same staircase in this mad scramble, and they end up on top of me. And they pull us up, and I'm shaking, and I'm mad. I am mad. I said, we don't belong in this building. So I get on the radio right away, and I call the division, and I tell the deputy, I says, Chief, this is a bad building. We almost had 3 guys killed just now. Get everybody out of this building. And I'm adamant about it enough, and finally he sends up a battalion chief, a guy named Harry Rogers, who was just a spectacular fire officer, very highly respected senior battalion chief in Brooklyn. And Harry comes up, and he looks, and he says, "You're right, this is a bad building. We don't belong in this building." So he gets on the radio, and finally when he gets on the radio and tells the deputy, we got to get out of here. You're going to get guys killed. Then he finally pulled us out. We got lucky. Nobody got hurt. We didn't belong in that building. It was a piece of crap, vacant building. It had been vacant for years. There was nothing to save and everything to lose. We just didn't belong there. Fortunately, the FDNY has long since revised its tactics for fires in vacant buildings and other structures where there is no civilian life hazard and no property of major value to save. All it took was an attitude adjustment brought about by a number of tragedies. Don't you pay for the same lessons? After several tragedies in the 1970s and 80s that killed and maimed a number of firefighters and officers, the FDNY instituted a program to inspect and mark every vacant building in the city, and there were lots of them. The markings indicate the hazards present and tell the firefighters what type of attack should be conducted. The building is marked with a box painted at all entrances. If the box is just an empty square, that means the building is of normal structural stability and interior operations may be conducted with caution. If there is a single line drawn diagonally across the box, this indicates a building that has some hazards, such as holes in the floor. All operations should be conducted from the exterior if possible. Interior operations might be conducted in a building with 1 slash if the fire is small and a careful examination shows that such an operation is safe. Finally, if there's an X through the box, it indicates a building with severe hazards, and no interior operation should take place. At vacant structures, the use of exterior streams is preferred at all times. What you've always got to keep in mind is that we are the only life hazard at a vacant building. Now let's discuss fire-related emergencies. A large percentage of all fire department responses involve situations where there is no fire present or the fire is still within its normal container, but there's still a need for emergency assistance. We call these incidents emergency responses. Gas leaks are among the most common of these emergencies. Natural gas is formed as a result of nature's action on organic materials over millions of years. Texas, Oklahoma, California, Louisiana, and West Virginia are the largest domestic producers of natural gas. It is carried nationwide via pipeline for distribution to consumers. Natural gas is primarily made up of methane, which accounts for more than 90% of its total volume. The other 10% is ethane and carbon dioxide. The presence of ethane in natural gas is often used by fire departments and utility companies to pinpoint the source of gas odors. A sample is taken and analyzed in a lab. If the sample contains ethane, then the source could be a natural gas leak. If it does not, then the source of the odor isn't natural gas, but could be swamp or sewer gas or another hydrocarbon vapor. Natural gas, as it comes from the well, is colorless and odorless, but we've all smelled gas before. This happens because a powerful odorant made of mercaptan and sulfides is added to the gas for domestic use. This odorant is so powerful that as little as a quarter pound of the liquid can treat up to 1 million cubic feet of natural gas. Obviously, that's some powerful stuff. Natural gas emergencies can be divided into three basic categories: inside leaks, outside leaks, and leaks resulting in fires. Although they all present unique dangers, the inside leak is the most dangerous due to the potential for explosion. Outside leaks would be the next most dangerous. Gas can seep into buildings, manholes, or other spaces and cause an explosion. Gas that has already ignited poses the least amount of dangers. It may ignite nearby exposures, but there's very little chance of an explosion. Natural gas gets shipped all over the United States via large diameter, high pressure transmission pipelines that operate between 350 and 850 psi. Remote sensors monitor pressure, and operators in central control locations can usually detect and isolate any leak using remote control valves. Even after the valve has been shut off, however, gas will continue to leak for a while due to the amount of gas present in these large diameter pipes at such high pressures. Most gas burning appliances operate at 1/4 of 1 psi pressure, so the pressure has to be lowered significantly before it gets to your house. From the transmission pipelines, gas passes through city gate stations, then local district regulator stations that further reduce the pressure within the distribution system down to that 1/4 of a psi range. These are low pressure gas mains. In some newer systems, pressure in the street mains is higher, but gas appliances still require that 1/4 of 1 psi pressure, so the pressure must be reduced at each building by its own regulator. There are two kinds of regulator, spring-loaded and dead weight, and both are subject to failure. If this happens, excess pressure can make existing burner flames much higher, and they can ignite nearby combustibles, or the flames may be blown out and gas allowed to flow into the building. If a regulator is located inside the building, it will have a vent line piped out through the wall to what is called a PEC vent or a Fisher vent that allows most of the excess gas to vent safely. You should be able to recognize a regulator failure by the gas odor as well as a hissing sound coming from the vent line. If you encounter a serious gas emergency, such as a regulator failure, the first thing you should do is notify the utility. Next, you should try to shut off the gas using the curb valve or the service entrance valve. As a general rule, it is usually best to use the valve closest to the problem to control a leak, as that allows the rest of the building to continue to function, which may be critical in cold weather. If a severe leak occurs, however, it might be necessary to use the service entrance or curb valves, since these are often quicker and do not require firefighters to enter the gas-filled structure. A service entrance valve is found on larger, multi-tenant occupancies, such as apartment houses and strip malls. It provides a single point of control for the entire building instead of having to shut down numerous valves in an emergency. The curb cock is usually a buried valve on an underground gas line. As its name implies, it is usually located between the curb and the building line. There are several different shutoffs located along the gas system. Some may be used by firefighters, while others should only be operated by utility personnel. Starting at the appliance and working back toward the source of supply, these valves are as follows. The appliance cock. It is most often a quarter-turn valve located immediately adjacent to the gas-burning appliance. It can be used to isolate a single malfunctioning device while leaving the rest of the building in service. The next point of control would be the meter cock, which controls the supply to one entire customer, usually an apartment or a single business. This may be inside the occupancy that it serves. Street valves include any gas valve located beyond the curb line. Street valves should never be operated by firefighters except under the direct control of an authorized utility representative under emergency circumstances. Street valves control the flow of gas to entire neighborhoods and often do not control flow to buildings they are located directly in front of. Closing a street valve may cause a greater problem than it solves. All of the above valves might be used by fire personnel in an emergency to stop the flow of gas. Then, start searching the involved premises for fire extension, any dangerous gas buildup, or any victims that may be overcome. Finally, vent the area if necessary and safe to do so. What action should you take in the event of a natural gas leak inside a structure? The first priority on report of a gas leak is to notify the utility. This should be a predetermined action by the dispatcher. The dispatcher can also start working on steps 2 and 3 by asking the caller when they first notice the smell and how strong it is. A strong smell, or one that suddenly appears, indicates a potentially serious situation, and the dispatcher should advise the caller to leave the premises and wait outside for the fire department. All that is required to ignite an explosive gas-air mixture is the tiniest spark or open flame, so you must eliminate all sources of ignition. Light switches, doorbells, cell phones, and even your own portable radio are potential sources of ignition. Anything electrical can be a potential source of ignition, so shut off power to the house if it can be done safely, which means outside the gas-air mixture. A combustible gas detector is an essential tool at any incident involving gas. Since deodorant may have been filtered out by underground leaks, and even the best nose can't differentiate between 3 and 4% gas in the air. Firefighters who are searching the building for occupants, the source of the leak, and the location of the shutoffs can usually vent at the same time. Don't overcommit manpower. Just send enough people to do the job and keep everyone else on standby in a safe location where they won't be exposed if the building does blow up. Where to vent is usually simple. Gas is lighter than air, so vent in the upper areas. When venting, don't cause unnecessary damage. Opening windows is usually sufficient. You rarely need to break them. One afternoon, we go to a gas leak in a big department store, probably 300 by 600, like the size of a Walmart now. So we get the explosive gas detector out, and we get 100% of the lower explosive limit right at the front door. Means any spark at all is going to blow this entire building right to the ground. So we're really not happy. We go inside, and inside, the gas is even more concentrated. It had been blowing for probably 15 minutes now. And we look, and there's just no way we can stop the leak. We think about trying to ventilate, but we decide against ventilating at that point, which is a good thing because the gas concentration in that store was well over the upper explosive limit. It was just too rich to burn, which comes into play here in a second. It was a tremendous decision. We back everybody well away from the building, and we got everybody hiding behind the apparatus in case this thing does blow up. The plate glass windows don't blow out and cut everybody to ribbons. So while we're out there waiting for the utility company to shut the gas off, the electric utility arrives first. And we tell them, well, we want the electric shut off too, remove all the sources of ignition, So they're going to cut the electricity way out at the street, which is a couple of 100 feet away across the parking lot. And when they cut the electricity, all of a sudden, all the emergency lights, the emergency exit lights, come on in the building, all over the building. There are now scattered lights popping on all around the building. Every one of those was another potential source of ignition. Every one of those was an electrical spark that could have ignited that gas, except it was too rich to burn in that building. If we had vented first and then cut the electric, we could have blown that entire building to kingdom come. The decision to send personnel inside should only be made after considering the risks. Unless there is a known life hazard present, treat the situation as a potential time bomb and expect the worst. Use the minimum amount of people needed to do the job and make sure they are properly equipped with SCBA, forcible entry tools, explosion-proof lighting, and a pipe wrench. Although they aren't as common as indoor leaks, outside gas leaks can be just as dangerous. Once it has escaped through the leak, gas will take the path of least resistance back to the atmosphere. Often, that path is along the gas service pipe or another underground line. This type of migration is insidious because as the gas travels through the ground, the soil filters out the odorant. That means that the gas will be undetectable to even the most seasoned firefighter. Many outside leaks are caused by contractors excavating in the area. The best course of action is to immediately notify the utility. Always approach a leak from upwind. Locate and stop any potential sources of ignition. Check the basements and cellars of nearby buildings with a gas detector and ventilate and evacuate any that show any gas buildup. Check quickly at the main entrance, then move to the points in the cellars where the gas pipe and other utility lines enter the building. Once you've done that, stand back and wait for the utility to fix the leak. Winter can be particularly dangerous because the frost line effectively puts a lid on the soil, making migration more likely. And gas lines are also more subject to stress during periods of freeze and thaw, making them more likely to fail. One final thought to remember is that no member of the fire department should ever try to stop a leak in a plastic pipe. If absolutely necessary, you may attempt to stop leaks in smaller, low-pressure steel pipes using the varying plugging and patching devices, but avoid plastic piping at all costs. Whenever fluid travels through plastic piping, it builds up static electricity. A plastic gas pipe can hold a charge of up to 30,000 volts. If you grab that pipe to apply a patch, it will probably discharge that current and cause a spark, igniting the gas around you. Operations of gas fires should be similar to indoor and outdoor operations. As always, your first action should be to call the utility company. Control evacuation, protect exposures, and then just let the fire burn until the supply of gas is shut off. If it's necessary to reach a valve or to save a life, small fires can be extinguished with dry chemical, halon, or CO2. Larger fires may require a fog stream to reach the valves. Use care when placing hose streams where excavations have ruptured the gas line. You'll want to keep unnecessary water out of the pit, since utility crews may have to work in that area later to stop the leak. Liquefied petroleum gas, or LPG, is a mixture of several different hydrocarbon gases. It's mostly propane, but it may have some parts of butane and ethane. Depending on the time of year and what part of the country you're in, the exact percentages will vary, but the greatest percentage will nearly always be propane, so that's how you can expect it to behave. Propane has a wider explosive range than gasoline, 2.1% lower explosive limit and 9.5% upper explosive limit. Propane turns into a gas at minus 44 degrees, so it will always be ready to ignite if the conditions are right. Propane is heavier than air, so it tends to sink to lower areas, but air movement may result in explosive concentrations at nearly any point in an enclosed room. When this happens, it's called a vapor-air explosion, and it can level a substantial building. Unlike a BLEVE, the gas in a vapor-air explosion has had time to spread out farther and mix with more air, thus enlarging the area that ignites, and increasing the pressure that results. One such explosion in Brooklyn killed 3 people when a 20-pound barbecue tank fell down the flight of stairs into the cellar of a plumbing supply store. The cylinder's valve was broken off in the fall, and it emptied its gas, filling the entire cellar with gas before finding a source of ignition. The resulting explosion leveled 3 attached brick buildings and damaged 2 others. Liquefied propane cylinders contain propane in both the liquid and the gaseous states. When it's compressed enough, propane gas turns into a liquid. In doing so, it shrinks down to 1/270th of its original volume as a gas. That makes it extremely convenient for shipping and storage. When the pressure is released, as happens when the valve is opened, the liquid begins to boil off into a vapor. As it does, it starts expanding back into the gas at 270 times its liquid form. It is this rapid expansion of liquid into a gas that can wreak havoc in a confined space. Consider a leak in a confined space of a single quart of liquid propane, or about the same amount found in a common hand torch. That single quart will evaporate into 270 quarts of pure propane vapor. That vapor, then mixed with air, is enough to create 12,857 quarts of explosive gas-air mixture. However, the first thoughts of many firefighters regarding LPG are of a different type of explosion, the BLEVE. A BLEVE, or boiling liquid expanding vapor explosion, is a particular threat to firefighters, since it often occurs after we've arrived. Most propane leaks don't become violent vapor air explosions. Either the gas ignites immediately, in which case there is a fire, or the occupants stop the leak and prevent ignition. Once the gas ignites, however, a chain of events begins to unfold that has been repeated many times. The first thing that happens after ignition is that fire exposes either the gas cylinder involved or other nearby cylinders. As mentioned before, LPG cylinders contain propane in both its liquid and vapor states. Like all liquids, the LPG sits at the bottom of the container and the vapor occupies the top. The liquid propane acts as a coolant, so as the shell of the cylinder is heated, the area in contact with the liquid is kept cool by the propane inside it. The heat being absorbed by the liquid raises its temperature, causing it to boil faster and increasing the pressure on the gas at the top of the cylinder. The pressure inside the cylinder is directly related to the temperature of the liquid inside. At 70 degrees, the pressure in the cylinder is about 100 psi. At 100 degrees, the pressure skyrockets to 190 psi. If the temperature continues to rise, so does the pressure. At the same time, the steel at the top of the cylinder is being weakened. Eventually, the cylinder reaches its failure point and a BLEVE occurs. A BLEVE results when a liquid above its boiling point is released suddenly from its container, and a superheated liquid expands rapidly. The resulting release of energy can launch parts of the container in any direction. Cylinders that BLEVE can be launched long distances. Gases aren't the only problem that firefighters face. During the winter months, you will be called to numerous emergencies involving oil-fired heating systems. To perform our duties well at these incidents, we should have a working knowledge about the oil itself as well as the equipment it fuels. Fuel oils come in several different grades, rated from number 1 to number 6, depending on the fuel's flash point, among other factors. Since no one wants a 275-gallon tank of highly flammable liquid in their house, fuel oils have flash points that are relatively safe. Number 1 oil is the lightest of the fuel oils and has the flash point of about 100 degrees, similar to kerosene. Number 2 oil is most commonly used in 1- and 2-family homes. It also has a flash point of 100 degrees, but it contains more impurities than number 1 oil. Number 3 oil is an intermediate grade of fuel that is no longer widely used. Number 4 oil is normally used in mid-size applications, like apartment buildings and factories. Even with a relatively high flash point of 130 degrees, number 4 oil still requires no preheating. Number 5 oil also has a 130-degree flash point, but it contains more impurities than number 4 and may require some preheating to get the oil to flow easily. Number 6 oil is the heaviest heating oil with a minimum flash point of about 150 degrees. It will require some preheating to get it to burn. When these heavier oils are stored, unused steam or hot water from the boiler is piped to heating coils within the storage tank. These heating pipes serve to preheat the oil to temperatures of up to 212 degrees, so you should be very cautious when operating around these tanks or piping. Also, be aware that some of these oils are stored above their flash point, so any release will result in flammable vapors, looking for a source of ignition. The modern oil burner consists of a firebox and a high-pressure oil gun. The burner receives its supply of oil from the tank, burns the oil, then transfers the heat to a useful place. Any products of combustion are then vented up the chimney and out to the atmosphere. The components of an oil burner are divided into two systems: the oil handling and the control systems. The most common burner is the high-pressure gun type. Oil is drawn through a pipeline to the oil pump in the gun. This pump supplies oil to the nozzles at pressures ranging from 100 psi in homes to 300 psi in large installations. The high-pressure discharge acts much like a high-pressure booster line, atomizing the oil into very fine particles and exposing more surface area to combine with oxygen. This gun also contains a fan to blow fresh air through the oil spray at the same time. At the end of the gun is a source of ignition, either a gas pilot light or two high-voltage electrodes that create an electric arc. All that we need now is a signal to light the pilot light and begin the chain reaction, thus producing fire. The main control for the system features a running circuit and a starting circuit that control operation of the fuel pump, the fan, and the ignition source. It also has a safety circuit that shuts down the pump and fan if the igniter malfunctions or fails to light after 90 seconds. The most common limit control is an ordinary thermostat. When the thermostat senses a demand for heat, it goes to the on position. When the heat demand has been satisfied, it goes to the off position. There are two other limit switches that you may encounter: a pressure troll and an aquastat. The pressure troll is used in steam systems to keep the pressure within an acceptable range. The aquastat works much the same way in a hot water system, keeping the water temperature within set limits by controlling the burner. There are a few problems you could encounter with regard to oil burners. The first, and probably the easiest to handle, is the smoking burner. To burn cleanly, oil requires the proper dispersion and the proper ratio of fuel to air. If anything interferes with this ratio, clogged nozzles or air supplies, worn-out pump or fan motors, or improper or contaminated oil supplies, the result is likely to be soot. The procedures for this type of incident are relatively simple. On arrival, check the chimney for thick smoke. Burners operating correctly will burn fairly cleanly. Be sure to conduct a size up and verify the occupant's cause for alarm. Then locate and turn off the emergency switch. Then turn off the oil tank valve, cutting off the supply of fuel. Once the valve is turned off, verify that the cause of the smoke was minor. Finally, advise the occupants that they need to have their burner adjusted by a qualified serviceman. The second type of incident to which firefighters are often called is a delayed ignition, or kickback. In this case, the thermostat calls for heat and begins the start cycle. Oil and air are discharged into the firebox, but for some reason, ignition doesn't occur immediately. Oil vapors will fill the chamber and travel up the smoke pipe. At the same time, the primary control is trying to recycle the startup procedure. If it is successful in producing a source of ignition, the entire vapor cloud will ignite at once, causing a loud thud which could knock the smoke pipe loose or blow open the burner door. Either one will allow smoke to enter the burner room, and burning oil could have pooled in the firebox or spilled out onto the floor. At such incidents, always take the following steps. First, shut off the remote control. Then carefully enter the basement to examine the area around the oil burner. You should always stretch a hand line for backup, just in case. If some oil has ignited outside of the burner housing, you may use a portable extinguisher, either dry chemical or CO2. If the fire is within the firebox, let it burn out. Be careful not to get water or foam into the firebox. Cold water or foam could cause red-hot cast iron to shatter, releasing steam or scalding hot water. Next, you'll want to ventilate the area to clear out any combustible vapors. Turn off the oil valve at the tank so no more fuel can feed the fire. Check around the immediate area and make sure the fire hasn't spread. Finally, advise the occupants that they need to have a burner adjusted by a qualified serviceman. The least common burner-related call you're likely to receive is also the most dangerous. It's called the white ghost. A white ghost is a cloud of vaporized oil and air that has been heated above its flash point, escaped from the firebox, and is looking for a source of ignition. The white ghost is more common during long cold spells, when a burner has been running at peak capacity for extended periods. When that burner shuts off, then is quickly called on for more heat, there can sometimes be a delay in ignition. During this delay, the highly heated walls of the firebox can vaporize the oil-air mixture, causing it to expand and fill the surroundings with a highly flammable combination of heated oil vapor and air. That flammable combination appears as a fog-like mist, which can cause an explosion that can blow down walls and floors if it finds a source of ignition. If you encounter this kind of situation, immediately take the following steps to prevent ignition and protect life. First, evacuate the entire building immediately. Do not enter the cloud for any reason. Using a fog nozzle, open in a wide pattern for protection, locate the remote control and shut it down. You can cool the heated mixture with the fog nozzle, and it may also saturate the cloud and disperse it somewhat. Ventilate the area, but be aware that electric fans may cause a spark when plugged in or turned on. Search the area for anything else that could ignite the cloud. Any electrical system in the building, along with tools you may be carrying, like radios or cell phones, could ignite the white ghost. Finally, you need to shut off the fuel supply after the cloud has been dispersed. Once the cloud has been dispersed, direct the owner of the building to have the burner inspected by a qualified service technician. In recent years, another non-fire emergency has emerged, causing numerous fire department responses: the carbon monoxide detector. In the 1990s, self-contained, battery-powered detectors became available to the public at a reasonable cost. Most of the responses to CO detectors will be minor, non-life-threatening incidents, but I have carried out several victims that have been overcome, and even more bodies. All these incidents must be treated as potentially lethal, even if the vast majority are due to faulty detectors. If you respond to a call and find an activated CO detector, your first step should be to ask the occupants if they feel ill. CO exposure often produces flu-like symptoms, including fatigue, headache, nausea, dizziness, and confusion. If anyone reports these symptoms, evacuate the building immediately. Once you have removed the potential life hazard, it's time to locate the source of the carbon monoxide. First, ask the occupants what fuel-burning appliances were in use before and during the time the detector was activated. Then, start your meter readings at the front door, working your way to the location of the CO detector. These tests should always require at least 2 mask-equipped members with 2 CO meters and at least 1 portable radio. Record all readings by parts per million, location, and time. Check around every fuel-burning appliance as well as any chimneys. If you encounter a leaking appliance or flue, shut it down, but continue taking meter readings. There could easily be other sources of carbon monoxide. After you've completed your readings, begin ventilating the area. Inform the owner of any sources of CO found and the need to keep it shut down until it has been repaired. Once the CO readings have dropped to an acceptable level, usually under 9 parts per million, the building may be turned back over to its occupants. Wood-burning stoves involved in creosote fires can become a source of fire extension. A severe creosote fire can rapidly reach blowtorch proportions and can damage a chimney to the point it will allow fire extension to the structure. If you encounter a creosote fire, the first thing you should do is shut down the air intake to the stove. If there is no air intake shutoff, or if severe fire exists in the chimney, you will have to extinguish the fire to prevent extension. There are commercially available fire extinguishers that can be placed in the firebox and ignited, thereby suffocating the chimney fire. You could also use an ABC dry chemical type extinguisher by firing it up through the firebox opening, but this method can create an awful mess. One other method you could try is filling plastic sandwich bags with ABC dry chemical powder and then dropping them down the chimney. As the bag falls, the plastic will melt and release the powder, extinguishing the fire. The broad variety of responses that the fire service deals with each day has many variables, but one common factor: the potential for death and injury. Pay attention to your job at every incident, from the largest structural fire to what seems to be the most minor nuisance call. That will keep you alive. I'm John Norman. Stay safe.